What I want to think about today is thicker layers, and we can imagine that there are several possibilities of what we can do. So we can either add a material to the top, we can change the material in the surface, and we can do what we've been doing up till now, which is a combination of the two. So effectively we can form a new layer that's related to the base material and some kind of reaction at the surface. There are several ways to do this, to apply a new film to the surface, but if we're not using any material from inside, we're going to have to get it from the gas or liquid phase onto the surface, and that will be some kind of thermal spray like technique. If we're going to put some material inside our surface, then we're going to have to shoot it inside or get it to diffuse inside somehow, and if we're going to add it to the surface, then we need to if we're going to react it to the surface, then we need to have some wet or gas phase reaction that's going to do that. And obviously we've talked about oxidation already, but there are others. So let's start here and go here. Let's start off with a comparatively simple one. It's not a very simple one, but it's a comparatively simple one. We've got a zinc with a zinc oxide hydroxide layer on it. That's our piece of maybe galvanized steel or something, and we want to treat it to make it a little bit more resistant and also to accept paint better. One of the possible ways is to generate a phosphate layer on the top, which we will do by putting the zinc 0 into phosphoric acid, H3PO4, and that will then etch the surface but also deposit zinc phosphate. So the acid will etch away the zinc oxide and it will deposit zinc phosphate. Zinc phosphate is comparatively insoluble, and so it will be hard to remove, but it's also but it also forms as a rough crystalline layer on the surface, and so it's easier to key things into it like paint. So that's very handy. It's not impervious, however, so typically in the old days there was a second treatment with chromate. These days it's not used like that. So then we would get zinc with a different zinc oxide, so it's not the same zinc oxide layer. We have some kind of intermediate layer, and then we've got phosphate, and the phosphate is much thicker and very rough. This is a fairly common process, particularly in automobile engineering, that kind of thing, but we also need to retreat that to stop it from being impervious, so that can continue to corrode. We also need to get rid of excess acid. In this next example we switch to aluminium. Aluminium has its own little thin oxide layer, and what we're going to now do is apply a voltage, but we're going to do it in sulfuric acid. Normally commercially it's a proprietary mixture of acids, but sulfuric acid works. That dissolves the aluminium dioxide off the surface at a certain rate, and we can grow new by applying a voltage. Let's make this negative compared to something else. Let's have it over here. Let's make it platinum. It won't really be platinum, but we'll make it platinum so that nothing happens. I've made it the wrong voltage. It has to be positive, because we want the aluminium to corrode. We want it to become Al2+, so we're making aluminium ions, and they will be interacting with the water. So if we have water in here, that will be generating aluminium dioxide. This generates an interesting effect. So normally we would expect much the same as we would if we heat it up, but we have a slightly more exciting effect. Because we're generating an oxide layer, and the oxide layer is bigger than the aluminium, so we're making aluminium ions. It makes aluminium dioxide. That generates some stress, and the stress causes a rippling effect to happen, like this. And the rippling effect is interesting because it causes the the more curved parts of the aluminium dioxide, the more stressed parts, to dissolve faster. Those are the ones at the bottom and a little bit on the top to start with, and when it's opened it's not connected anymore, so effectively this breaks and shoots off, and we end up generating, if we do this properly, in inverted commas, we end up generating deep pits which are made of oxide, and at the bottom there's an oxide layer. We can make a defined thickness of oxide by choosing the voltage, but that's the oxide on the bottom, and the thickness here is determined by how fast the acid is etching compared to how fast we're making it. So we can vary the parameters, the concentration of the acid, the voltage, and we can make different oxide layers, different thicknesses. And in the case of aluminium, they're all porous, and the porosity is handy in this case because we end up with effectively deep pores like this, and the deep pores will be comparatively easy to fill with dye or something. So what we can do is fill them with dye and create normal anodized components like this, for example, and we can also heat them up and cause the sharp corners to melt, or not melt, to dissolve and then redeposit, and that blocks the ends typically. So as we can see from this rough table, phosphating with some kind of phosphating mixture is good on ferrous metals, so iron and steel, zinc, aluminium, cadmium, in special cases, silver and tin. That generates an insoluble phosphate layer that's slightly soluble in acid but not very soluble in higher mid to high pHs. Then anodizing is not so good on most of these metals, but aluminium, titanium and magnesium in particular are very effective because we only get an oxide layer. The zinc oxide is fairly unexciting. Iron oxide is not very protective at all. Cadmium oxide is not a big advantage. Silver oxide is rare, and you typically have to have a different silver compound if you want to protect silver. And tin oxide it forms on its own. So we have two techniques which generate an inorganic material out of the substrate, which is typically a metal, and that can be used for colouring, which is what we had with the anodizing, but it can also be used for colouring with the phosphate because we can use it to attach a paint layer. We can attach paint to an anodized layer, but we can also dye it. So if we want to paint aluminium, we typically have to do something first, and anodizing is one of the ways to make it receptive to paint. Then it's good, both of these techniques are good for corrosion protection, for wear resistance because they're hard, they generate a hard material. And if we think of these metals, okay, iron can be, or steels can be very hard, but zinc, aluminium, silver, cadmium, tin, titanium are very soft metals. So if we want to protect them from wear, we need to coat them with something, or need to protect the surface with something. This is not really a coating. That generates a bit of hardness to protect against wear and scratching, and lubrication is there because both of the coatings are porous, and we can fill them up with some kind of oil, grease or similar. So in the case of zinc phosphate, it's very often a zinc stearate, which is a type of soap, and that is a lubricant, and you can use that for processing tasks. If we want to stretch the piece of zinc, we need a little bit of lubrication, and it needs to spread over the surface, and this is a very good way of doing it. If we want to make an aluminium part lubricated, it's quite difficult, and we can create a store of lubricant in those pores. Now if we want to insert some kind of material into our structure, it seems weird to start with, but let's take an example and then we'll understand. If we take case hardening as an example, case hardening is an old medieval practice where you take a piece of mild steel, a piece of iron, which is comparatively soft, so we don't want cast iron, we want enough carbon and little enough other elements in there so that it's a little bit ductile, and then we want the surface to be very hard, so we apply some heat treatment and we apply some carbon from the outside. So we would have, typically we would wrap it in cloth or something like that that's going to go in charcoal and carbonize, and then coat it with maybe some clay and then heat it up in a fire. It was usually a fairly hit or miss procedure depending on how old or how early it was done, but obviously it has developed into a technically advanced process, and it generates a hard layer of iron carbides near the surface. So this is also a conversion layer, but typically we're not going to generate a layer of pure iron carbide, we're just going to generate some higher carbon density near the surface, which generates a harder surface layer that isn't chemically massively different. That's the historical version, although there were then other versions with nitrogen, particularly in Europe, using things like guano as a nitrogen source to generate a nitriding layer. If we want to do that in a more modern way, we can do it using a measured process. This is a diagram of the process. We take our metal part. We first of all have to remove the oxide layer because it's quite hard to get foreign atoms through the oxide layer. Then we apply our new element to it and we generate a hard layer at the surface. So we're effectively alloying the surface layer. The carbon version, the case hardening, the reason that it was discovered first is because the application of carbon to the surface of iron will automatically reduce the oxide. That's how the iron was produced in the first place, by a reaction with carbon to form iron, carbon monoxide. That means that it can all happen in one process, but if we're going to do this with nitrogen, then we're going to need some way of attacking this, and one of the ways to do that would be to add some hydrogen. If we add hydrogen, we can also reduce iron oxide back to iron. It's a little bit better reducing agent than carbon in some ways, so it's not going to do anything else. The problem with using carbon is obviously we're stuck with carbon then. If we use hydrogen, we can reduce the iron oxide back to iron 0, and then we can apply our nitrogen. So we would need to have a mixture of nitrogen containing gas and hydrogen. The nitrogen containing gas could be nitrogen, but it could also be ammonia. This is a process that will take us all the way to engineering, because the main reason why these processes are useful are practical reasons. The practical reason why a nitriding layer is very effective and useful is that it's comparatively deep compared to a coating that we put on. So if we want to oxidize the surface, for example, or apply a new coating, nitriding can be comparatively deep. But more importantly, from a processes point of view, so those of you who've interacted with our engineers particularly, if we want to make a part out of this iron, and we want a hard layer at the top, which is going to be of the order of micrometers, depending on what we want it for. It can be many micrometers, can be a few, but it's on that kind of size range. If we want to do that, then we need to make our part first, because otherwise we're going to remove the hard layer. It is very, very hard, which means if we do it first, it's going to be difficult to machine it anyway, so that would also be a really bad plan. But the problem then is, obviously, if it changes the size of our part, then we may have to do some post-preparation that's going to be difficult and expensive. For practical reasons, what we want is a process that doesn't change the part size very much. And nitriding is an excellent example of that, because we're inserting nitrogen atoms inside the crystal structure of the metal, of the steel in this case, and that will make it harder near the surface. So if we make the part to pretty much specifications beforehand, and we allow it to cool, and then we can measure it, then we can be pretty sure that it will work, heat it up, nitride it, and go back again. That's obviously very effective, and we can get things to work. But how are we going to get the nitrogen to go in? So I've just mentioned heating it up. That was the original way with carbon. We need to get the solid state diffusion to start to work so that we can get it away from the surface. If we do that, we can control the thickness of this hardened layer. We don't want it too hard, because then we will make it brittle. If we make it not thick enough, it might wear through. So we want to be able to control that layer very well, and we can do that by using a nitriding oven like they make near our university. A different way to get the nitrogen or carbon, but mostly nitrogen, into the metal is using a plasma. So we've discussed plasmas before. We can make an ion out of the nitrogen and we can shoot it into the metal. That's very handy, and it also opens up a new window, because first of all we don't need to heat up our sample very much, and then it will stay close to the surface. We can control the energy of the ions by accelerating them to a chosen voltage, so we have more control parameters than we did before with just heating it. If we heat it, we're going to get a diffusion pattern into our surface. If we use ions, then they're going to get a certain depth, and that is going to be it. They will still get less and less as we go in towards the inside, which is useful anyway, because we don't want a sharp barrier between the hard and the softer material, because then this part will tend to fail at that interface. The other advantage of plasma is that we can apply a plasma to this stage as well, because obviously if we're going to heat it, we might as well heat it for every stage. If we're going to plasma it, we might as well plasma it for every stage. And if we do that, we can address this oxide layer. So we can remove an oxide layer that's a little bit more robust, something like aluminium oxide. If we make it thin enough, using a wet etch method to get it thin and keep it cold, then we can knock it off with a plasma or an ion beam of argon, for example, and then we can add our nitrogen afterwards. It turns out that even argon ions that are not so reactive will also harden the surface of a metal, because effectively we are introducing errors into the surface of the metal. While we are talking about that subject, we should probably mention another thing, which is the effect of diffusion and alteration in the surface on diffusion. So if we take, So if we take something like Aztec Gold, which is mostly copper with a little bit of gold in it, that is how they used to make their large statues. Take some copper, add a little bit of gold, and then you do follow a process. Their process was to take the copper and gold and heat it up. If you heat it up, the copper mostly reacts at the interface with oxygen, and because the gold is gold, it's not very motivated to do that, so the copper diffuses out, leaving a layer just below the surface which is rich in gold. Then the Aztecs used to post-treat it by dipping it into hydrochloric acid, or possibly other acids, but hydrochloric acid is one of the ones that I've heard mentioned. That will take off the oxide layer and leave the part looking like it's pretty much gold. It won't look like pure gold because it's mostly copper, but it will look a lot more like gold than the base metal. For the Aztecs that was important because for their religious purposes it had to look like gold and not actually be gold. That was their religious purpose. Why does this relate to stainless steel? Well, stainless steel, as you know, is a mixture of iron and usually chromium, nickel and possibly vanadium, other elements as well, but it depends what stainless steel we're talking about. Typically the chromium is cited as the important element, the nickel is a secondary. So we've got a mixture of metals and it's going to do the same thing. The chromium is going to make its way to the surface and react with the air to form a chromium dioxide, CrO2, surface layer, which is pretty much resistant to dissolution, and for the stainless purposes it's not coloured. It is also thin enough that it conducts very well, and so we can make a good contact to our piece. What happens now if we molest our stainless steel? So if we put it in bad conditions. If we start to address it aggressively, so maybe we put it in salty water, we've put some salt into our pan, it's fallen to the bottom and we're heating it up. That's a bad thing to do. You're not supposed to do that because we've got a local area of very high chloride concentration and an area further away that has low chloride concentration, so we generate an electrochemical cell and that will tend to corrode our stainless steel. What we want from our stainless steel is that it recovers from that, so we want new chromium. So let's just make them dots. We want new chromium atoms to diffuse to the surface or to the interface here as this oxide layer is removed. That is made easier if we pre-treat the stainless steel. What we want is the surface to, or the metal near the surface, to let chromium through better, and one of the ways to do that is to move it around a little bit to make the crystal size smaller and to generate twins and to generate more eutectic, so that then the atoms of chromium have an easier time to make it to the interface. So we can find that if we take a piece of stainless steel and we do some kind of surface treatment to it, like shock peening, shooting bits of lead at it at high speed, that makes it better at resisting corrosion because the chromium in the metal can make it to the surface better. Obviously if we take a large layer off the surface, it doesn't do it anymore.